So let's talk about the last section, which is about exponential and logarithmic equations. Okay. So of course, now that we know these operations, we know the functions. We have seen some algebraic properties. Now the natural thing is, what if this thing starts to show up in equations? How do we solve the equations when exponentials and logarithms start to show up? An equation that has exponential expressions is called an exponential equation. An equation that has logarithms involved is called a logarithmic equation. Okay. All right, so I guess let me tell you what's the basic idea that we're going to take advantage of. Let's first talk about exponentials and then we'll talk about what to do with logarithms. So recall that the function y equals b to the x is 1 to 1. Okay, so what does that mean? If it's 1 to 1, it means that every time that you input so for any two different inputs, you always get two different outputs. Or another way to say it is, if two outputs are the same, it's because the inputs are the same. In other words, this translates into the following. So, i.e., if you have that b to the m equals b to the n, then what can you conclude? What can you deduce from here? Then m has to be equal to n. And this idea, we use it to solve exponential equations. Basically, what we're saying here is, if you have two exponentials with the same base that are equal to each other, then the only choice here is that the exponent must match. They have to be the same. Why? Because it's 1 to 1. Because if these guys are different, then the output of the exponential has to be different. Okay? But in this case, because 1 to 1, it tells you that m is equal to n. So we're going to take advantage of this whenever we can. Now sometimes it's a little bit cumbersome to try to use this idea, so we're going to use what we know about logarithms. So we will also use the fact that if you have the b to the y, or let me use m and n. If you have the fact that b to the m equals n, this can be rewritten as, how can I rewrite this using logarithms now? Let me use x because that way it's more clear. How can we rewrite this as logarithms? Log base b of n equals x. Okay. So what the way to think about this is that if you want to have access to x, then you can rewrite this as a log to liberate the exponent. Now x here is by 7. Okay. We're gonna take advantage of this. All right. So let's do examples so you can see. So examples, solve, and then let's see, let's do 4 to the x equals 16, x minus 2, and then let's do 8 to the 2x equals 1 over 4 to the 3x minus 4. So of course, if we want to solve this, that means that we're looking for what should x be equal to so that the statement becomes a true statement. Okay. Now, in these two examples that we have here, and I put them like this because we're gonna do them using the red box. Okay. And then we're gonna do other examples that using the red box are not really that straightforward, so we're gonna use the blue box. So, what's the moral of the story? The red box is telling you, as long as you can write both sides with the same base, then you can take advantage of that property. Yes, you can match the exponents. So the question is, whenever you have an equation like this, the question that you need to ask yourself is, do I have a common base? In other words, can you write both sides of the equation with the same base? And that boils down to asking, can I write my bases that this time are not the same with a common base? In other words, focus on 4 and 16. Can we write those two numbers as something to some power where that something is the same? What is it? What's the common base?
4 to 1 and 4 to 2.
Say that again?
So the common base is 4.
You can do a common base 4. Very good. So 16, you can write it as 4 squared, right? 4 to the 1 and 4 squared. Or you could also say, for example, if this was a 32, probably would have been more interesting with a 32. If this was a 32, what would be the common base? It would be 2. Because 4 you can write as 2 squared and 32 as 2 to the 5. Do you understand this? Okay, anyway, but here 4 is quicker because you can do 4 squared. But here we could have done also base 2. This one is 2 squared and this one is 2 to the 4. Okay? But base 4 is quicker. Very good. So, for example, here we don't touch this one. Now, the one on the right, I can rewrite it as 4 squared to the x minus 2. Why am I doing this? Because I want to take advantage of the property of having the same base. Okay? Now, before we do that, of course, we need to have 4 to the something. We don't have that here yet on the right hand side. And now we can use the property of exponents. What can we do with these exponents? What do you mean cancel the 2's? No, no. What can we do? No, there's no log here. This is an exponent raised to another exponent. What do you do when you have this case? You multiply the exponents, right? Remember this? That's this property. So that's this property. Property number 5 right here. When you have the exponent of an exponent, you multiply the exponents, right? So that's exactly what we have right now. So we have 4 squared raised to the x minus 2. So now what we can do is we can multiply the exponents. So this becomes 4 to the x is equal to 4 to the 2 times x minus 2. Do you understand this? Yes? Okay, so now we are in a position that we can use the red box above. Now we have two exponentials with the same base, they are equal to each other. What can we deduce about the arguments? So the exponents in this case. What can we deduce from here?
They're equal.
And then x must be the same as 2 times x minus 2. Yes, and now you have a little linear equation, solve it. So we have 2x minus 4, so that means x, so x over here and 4 over here, so x equals 4. Okay? Questions? Do you understand this? Okay, so, of course, this method works as long as you can find a common base. When you can find a common base, it's a little bit, it's fast, it's quick, it's a nice little step you need to do. So sometimes you cannot find a common base, and then you need to bring logarithms and so on. That's the general way of doing it. We're gonna do more examples like those, but let's practice again with number 2. Let's see, can we find a common base here? Yes?
Wait, how did you go from x equals 2 times 4 to x equals 2?
So this x comes over here negative, giving you x, and this negative 4 comes over here positive, giving you 4. I basically swap these two, combine, right? All right. Let's see, number 2. Can we write that as a common base?
Can't you use 2?
Okay, how?
2 to the third.
Okay.
And then 2 to negative 2.
Very good. So here the a, so a and 1/4 they're not the same. But what we can do is a you can write as 2 cubed, and then 1/4 you can think of it as 1/2 squared, and then write that as 2 to the negative 2. So the 2 squared in the bottom bring it to a dot with a negative 4. Yes. So now we have everything as 2 to some power. Good. So we can write this as 2 cubed, and then this one as 2 to the negative 2. Is that okay? All right. So now, remember, you need to have 2 to some power. We are not there yet. So now the left-hand side becomes 3 times 2 is 6. So 2 to the 6x equals 2 to a negative 2 times 3x minus 4. And now, once again, we're going to use the red box that says if the two exponentials are equal to each other with the same base, then the exponents must be the same. And we finish solving. So we get 6x is going to be negative 6x plus 8. So x is 8/12, or So divide by 4, you get 2/3. Questions? Are you okay with this? Okay, but okay, fine. But what if, for example, what if this was a 5? Right? What if you have a to the 2x equals to 5 to the 3x minus 4? Now we cannot play this trick anymore, right? Finding a common base. It's not that straightforward to find a common base, like a nice little base. So we need to have another way of doing it. That's when the blue box come into play. Okay? Because basically the blue box tells you, okay, if you wanna solve for your x and the x is in the exponent, okay, write as a log. And let the log take care of business. Okay? So let's do that. So that was 1, 2. Now number 3, let me do a very simple one just to illustrate the idea, and then we do more interesting ones. So let's something as simple as 2 to the x equals 5. Okay. And to answer this question, 2 to the x equals to 5. If we could write 5 as 2 to a something, that's basically what we're trying to figure out, right? What is that something? We want to write 5 as 2 to a something. So, the equal base thing doesn't really work here. You could make it work always, but then you have to use logarithms anyways. So that's what we're using right now. Okay, so there are 2 ways to do this. I'm gonna do it, I guess, the most direct way, but then you will see that's not really that helpful, and then I'm gonna show you what's the general way. So basically, the most direct way is, okay, I wanna solve for x, just rewrite it as a logarithm. So if 2 to the x equals 5, what does that mean about x? What is this equal to?
1 base 2.
This is log base 2 of 5, and technically you are done. I mean, you solve for x, okay? The thing is, as you know, the calculator doesn't really, most calculators don't really have this. So then, we add this little extra step, and then, for example, we can give the answer as ln of 5 divided by ln of 2 using the change of bases. Do you understand this? Now, I want you to understand that this procedure doesn't really work when you have 2 exponentials. Okay, for example, here it works because we have one exponential here and a number on the other side. But if I were to throw in an x plus 3 in here, then we enter into a loop. Because if you try to do this, then yes, this x will be here, but then the x plus 3 will be trapped in this argument. And then when you try to get rid of the x plus 3, then you're going to get back to an exponential with the x trapped in the exponent. So you're going to be running into a loop. So that really doesn't solve our problem in the long run. So is there an alternative way of doing something like this instead of just rewriting as a logarithm? The answer is yes, there is, but we need to look at it from another perspective, which is the following. You want to solve 2 to the x equals 5. The idea is that you want to solve for x. Okay, I just need to bring this x down. Let's take advantage of property number 7. That said that if you have log, if you apply log here, that's going to bring the exponent down. That's what we want, right? So typically we use ln because ln, that's what we use to give our answers in typically. So what I do is I apply ln to both sides. Just like when you square both sides and that kind of stuff, if you have radicals, etc., well, I'm applying ln. Why? Because I'm going to use ln to bring the x down. Now use the property, you bring the x down. That's property of logs. That the exponents, you can bring it down. And now remember, ln of 2 now is just a number. So you divide by that. And we are right to the same answer, but now this idea allows you to deal with other exponents. If you have an exponent here, when you apply ln on both sides, you bring this one down, but the other one goes down as well. And then you can solve for the x. Okay? Which is what we're going to do in the other examples. Did you understand this? All right, so let's do a couple. So let's do 3 to the 2x minus 1 equals 10. Then let's do 5 to the x minus 2 equals 4 to the 2x plus 3. And then let's throw in this one, e to the 2x plus e to the x minus 6 equals 0. Okay, so for the sake of time, I'm going to do it. Okay. Remember, we still need to discuss logarithm. So solution. So let's see. Number 4. We have 3 to the 2x minus 1 equals 10. You could rewrite this using logarithmic form if you wanted to, but just to streamline this technique, I'm going to do it by applying ln to both sides. Okay. Now, for example, you could apply log of 3 to both sides. Nobody can stop you from doing that. Okay. It's just that I already said why you may want to use ln or base 10. It's for calculator purposes. Anyways, I'm going to apply ln to both sides. The reason for that is, by the way, everybody understands that the equality holds, right? If the two things are equal, because ln is a function, then ln on the left must be equal to ln on the right. Because same input has to give you the same output. Okay. All right. So now, using the properties, the 2x minus 1 comes down. Okay. And now just think of it, this is a number. So now, you can divide and move and so on. In fact, what I'm going to do is I'm going to distribute, that way we're going to nicely be able to solve for x. So I distribute ln, so you get 2 ln of 3, all of that times x minus ln of 3 equals ln of 10. So 2 ln of 3 times x equals ln of 10 plus ln of 3. So x equals ln of 10 plus ln of 3 divided by 2 ln of 3. Are you okay with this? Yes? By the way, notice that you can condense this, okay? For example, you can write this as ln of 30 in the top, and the bottom you can write as ln of 9. So if you wanted to, you could rewrite this as ln of 30 over ln of 9. And that would be less ln's that you have to compute if you wanted to evaluate this in a calculator, okay? And you can further condense this as log base 9 of 30, but then again, your calculator, you may not have the possibility of doing base 9. So this is, for example, an efficient way of computing this. Instead of doing, these three guys and taking care of all of this, all I have to do is ln of 30 and then divide it by ln of 9. And we get about 1.548. Okay, but I'm gonna declare this as the answer. But it doesn't matter. Okay, questions? Did you understand this? It's very important that you put these parentheses if you're gonna write x at the end. If you don't put the parentheses, it could be misleading, and it may look like ln of 3x, and that's not really what you want to say. You want to say ln of 3 times x. So if you're gonna put the ln in front of the x, put in parentheses so it doesn't get confused. Or if you want to avoid that, put x before the ln, and then it's clear that there is a multiplication. Okay. So I just wanted to keep it like that, just to emphasize that this is the coefficient of x. But you can just put 2x times ln of 3 when you distribute, and then there is no ambiguity, and you don't need the parentheses. All right. So that was that one. Let's do number 5. So number 5 was, so this is, I guess, the one that requires more painful algebra. Because now when you apply ln, you're going to have x's on both sides, and you need to start bringing stuff around. Okay? So just do it carefully. So we do ln. And again, I'm doing ln, but remember, you can do whatever log you want. Okay? So bring the powers down. And then we start working. So distribute 2x ln of 4 plus 3 ln of 4. Then collect the x's on one side, numbers on the other. Then factor out the left on the left. And now divide by the parentheses. So again, for computational purposes, if you want to actually evaluate this, it would be nicer if you condense the top as a single ln, the bottom as a single ln, and then it's easier for you to find the number in your calculator. Okay? But again, you don't need to calculate. This is the exact answer. This is what we are after. Okay? All right. Questions? Remember, all of these ln of 2, 5, and 4 that you see, these are numbers. So you treat them as such. Okay? So you apply ln, bring it down, and then these are numbers. So you distribute, and then you solve for x. This is a linear equation now. So solve for x as usual. Okay. Questions? No? All right. And then for the last one, let's see. We have e to the 2x plus e to the x minus 6 equals 0. Now this one is slightly different because we have the minus 6, okay? But that's okay, we can deal with that because it turns out that this one is quadratic in type. Even though it may not look like it, a priori, it is actually, you can think of this quadratic equation because you can rewrite e to the 2x as e to the x squared, right? So the moment that we do this, then, we can make a little substitution. We can let t be e to the x. So then with that substitution, then the equation becomes t squared plus t minus 6 equals 0, right? So now we figured out what t is equal to, but then once you know t, then we need to solve for x by solving this little exponential equation. So let's see, here we can factor this, that's t plus 3, t minus 2. So we get negative 3 or positive 2, right? Now we need to put back the original variable, which is x. So t equals e to the x. So that means e to the x is negative 3 or e to the x equal 2. And then let us examine this. So let's see, the first little equation, e to the x equals negative 3. What can you say about this? No solution. Very good. Remember, exponentials can never be equal to something negative, right? So this one has no solution. So nothing to do here. So ignore it. And now the other one, can we solve for x? What's x? This is just ln of 2. You can just write it in logarithmic form, right? So the solution to that equation is ln of 2. Questions? Are you okay with this? All right. So that's exponential equations. I mean, that's really, I guess the most complicated one could be complicated in the sense mathematical involved is something like this. When you have, different bases that cannot be really be put to a common base, and then with exponents on both sides, then when you do a ln, you have to be comfortable manipulating left and right. But other than that, this is as far as it goes. And from time to time, these quadratic in type cases, of course, it could be more complicated ones, but that's the essential of it. Now let's talk about logarithmic equations. Basically, exactly the same idea. We're gonna have our two boxes, but instead of dealing with exponentials directly, we're dealing with log. Okay. All right. So logarithmic equation. This is an equation containing logarithms. Okay. So the idea is, once again, to recognize the fact that the function y equals log base b of x is 1-to-1. So just like in the case of the exponential, we have the following. So if you know that log base b of m equals log base b of n, then what can you deduce? If you have two logarithms with the same base that are equal to each other, what can you deduce? That m and n are the same. So they have to have the same argument. Okay? So same logic as what we did for exponentials. And then also, don't forget the fact that if you have log base b of x equals y, and you want to solve for y, okay, let me write it as m. If you have log base b of x equals m and you want to solve for x, well, you can just rewrite this as x is just b to the n, okay? And then we just solve for x right here, okay? So always keep in mind that this back and forth from between logarithmic and exponential form is, is helpful. Okay, and then of course all the properties. So let's do examples. Okay, so let me say something else. So that means that when you are dealing with a logarithmic equation, it boils down to two things. If you have your equation and then you have a bunch of logarithms on one side and then number on the other, that means that you can use properties of logs to condense that side to a single log, and then you use the blue box. Because every time that you have a log equals to a number, then you're good to go. You use the blue box. Now, if you have an equation in which you have logs on both sides, what you can do is condense all the logs in each of the sides, right? And then you will have a log equal to a log, and then you use this property to get rid of it. Okay? And then you keep solving whatever you have left. That's the general idea. All right, so let's do examples. Solve, and let me write all the equations here. So let's do this one. Then we do this one. So these first three, they have log on one side, numbers on the other. And then let's do others in which, well, let me just write all of them. Let me use ln. I haven't used any ln. Okay, so here we have 6 equations. Let's solve them. There is something else that you have to keep in mind that we didn't really worry about when we're doing exponential equations, but you have to worry about now when we do logarithmic equations. There is a domain that you have to be concerned. Remember, exponential domains are real numbers. Doesn't matter. But for logarithm, whatever your solution is, you will have to make sure that it's in the domain of the equation. For example, here, this is telling me that x has to be positive. So whatever answer you give me better be a positive number. Okay? Do you understand this? Here, it's telling me that x has to be bigger than 1/2. So whatever answer you give me has to be bigger than 1/2, and so on and so forth. Okay? So sometimes it could be that when you solve an equation like this one, this is going to turn out to be a quadratic equation, really. When you solve it, you could get a positive and a negative. You have to be careful because then you have one of those solutions may not work for the logarithm, for the original one. Okay? So let's keep that in mind. So you always have to check back into the original expression to see if your solutions make sense. That was something that we didn't have to worry about in the exponential case. All right, let's solve these problems. So solution, remember, if you have a log equals to a number, you just rewrite as an exponential and then you finish over. Like in this case, it's very straightforward, right? We have a log equals to a number, the x is right here in the argument. Well, what does this mean about x? What's x equal to? 5 to a negative 2, which is just 1/25, right? It's really not much going on here. Let's go to the next one. So log base 3 of 2x minus 1 equals 4. Okay. So again, it's in general, it's always good to write down, your restrictions. Here, your restrictions is that x has to be positive. Here, the restriction is that 2x minus 1 must be positive, so x has to be bigger than 1/2. Just to make sure that whatever solution you obtain satisfy the restriction. If it doesn't, then you cannot consider a solution. Okay, again, here I have a log equals to a number. So to be able to solve for x, I first need to liberate this argument. I have to leave it alone. And we can do that by writing this as an exponential. So how can we write this in exponential form? What is this in exponential form? Okay, so I want the x on the left. So 2x minus 1 equals 3 to the 4. Anybody understand this? Okay, so 3 to the 4 is 81. So that means 2x minus 1 equals 81, and now you solve for x. So 2x is 82, that means x is 41. 41 is bigger than 1/2, so we're good. Questions? All right, let's go to the third one. So now it says log base 2 of x plus log base 2 of x minus 7 equals to 3. So remember, the goal is to have a single log. If you want to have a single log equals to a number, then we are in business. We can do what we did above. Okay? So what can we do here? How can we write the left as a single log? We use the properties, right? It's a sum, same base, we can write as a product. So now here is where the little exercises we were doing earlier, they come in handy. Okay? You can have a bunch of logs in the equation, doesn't matter, condense as a single log. Okay? And then you go from there. So here we can write this as log base 2 of x times x minus 7. And that's equals 3. Now we activate the process. So this means that x times x minus 7 is equal to 2 cubed. And now this is a quadratic that we can solve. So as x squared minus 7x is equal to 8. So x squared minus 7x minus a is equal to 0. All right, so as x minus 8, x plus 1. So here we get x equal a or x equals -1. And remember, before we decide, we claim victory in the sense that before we decide that we have a solution, we need to go ahead and check and make sure that these solutions, they make sense. So that was 8 or -1. And again, here I didn't write the restrictions before, so let's write it down now. So the first log is telling me that x has to be positive, and the second log is telling me that x must be greater than 7. Do you understand that? I mean, the second log is telling me that x minus 7 must be positive, so that means x is bigger than 7. Because it's and, because we need to be okay for both logs, okay? When you put them together, the restriction is x bigger than 7. Do you understand this? So when you have your solution, you have to make sure that whatever solution you give me must be bigger than 7. So is -1 a good solution? No, this is not good. This is, remember, this is called extraneous. It's an extraneous solution, but x equal a is okay. That's bigger than 7, that's fine. Questions? Okay. So again, just condense it as a single log and then, use the property. Let's see. Let's do the next one. So that's log base 6 of x plus 5 plus log base 6 of x equals 2. Let's see, who can tell me what are the restrictions? What restriction do we get here? So the first log tells me that x must be greater than -5. Everybody agree with this? Okay, is that it?
It also must be greater than 0.
And, this is important, and the second log tells me that x must be greater than 0. So when you put this together, what's the overall restriction? Greater than 0. Remember, you have to do the intersection. So what encodes both of these? Greater than 0. Yes? All right. So whatever we do, we better give a positive answer. So now to solve it, again, we just combine. So in this case, this would be log base 6 of x times x plus 5 equals 2. So that means x times x plus 5 equals 6 squared, which is a 36. So that's x squared plus 5x minus 36 equals 0. Can we factor this? 9 and 4. X plus 9, x minus 4. So we get x equals -9 or x equals 4. Is there anything that we need to ignore here? So -9 is not good. 4 is fine. Questions? Okay. Let's see. 2 more. So number 5 is easy. So this one is just to illustrate what to do when you have, logs on both sides. So far we have had logs on one side and then a number on the other. Well, if you have logs on both sides, you want to take advantage of the red box that says that if 2 logs are equal, that means with the same base, that means the argument must be the same. Okay? So let's just make it look like so. But before we do that, don't forget the restrictions. So what restriction do we have here? X has to be positive. Okay? Restriction means the domain of the equation. Okay? All right. So now we almost have already the 2 logs equal to each other. We just need to do something about these 2. What can we do about these 2? What can we do about it?
We can make it x squared.
We can bring it here inside. So we have a log equals to another log. Okay? So this now becomes log of x squared equals log of 25. Because the base is the same, then from here it follows that x squared must be 25. So x is either 5 or -5, right? But then we know it's greater than 0, so that guy has no business. It has to be positive. So let's do the last one, which is a little bit more, more complicated than this one. But the idea is exactly the same. So hopefully you see how we're using the properties of logs to solve the equations, okay? That's why this technique of condensing as a single log is important, so you can solve the equations. So it was ln of x plus 4 equals ln of x plus ln of 4, right? It was number 6. Yeah. Okay, so before we continue, restrictions. What's the restriction here? So x, what do you mean by -4?
Oh, was it greater than -4?
Bigger than -4? Is that it?
Yes.
Well, there is something more. And greater than 0. The -4 is this guy, but then this one is telling you, wait a minute, -3 is not good, -2 is not good. It has to be greater than 0, right? So when you put them together, the restriction is x greater than 0. Okay, good. So now let's solve it. So again, the idea is let's have single logs. The left is already a single log, so nothing to do there. Let's keep it like that. Then right, we combine. How? Multiply, right? ln of 4 times x. And now, because we have 2 ln's that are equal to each other, that means x plus 4 must be equal to 4x. You okay with this? And now we solve. So what do we get? 4 is 3x, so x is 4/3. 4/3 is bigger than 0, so we are good. Okay, questions? Yeah, 4/3. Are you okay with this? All right, so I guess with this, we are done. The other thing is applications, but applications is basically just knowing the formula to model the problem. So in the review, you have exercises with application, but you don't have to develop the formula. The formula is there for you. All you have to do is, solve it. Okay? So you should be able to do that.